Alright, so welcome back, Calcsters. In this video, we're going to continue our discussion on the fundamental theorem of calculus. Now remember, the fundamental theorem has two very distinct parts. The first part tells us that we can take an integral, or a derivative of an integral, and we have that dummy variable, typically d of t, and f of t, d of t. And then when you take the derivative, it just changes to x. Now that only works, really important here, the only time that first part works is if you're going from some constant to just x. This is part one of the fundamental theorem, which you guys already have in your notes. If you take the derivative of this thing, well, this thing winds up being f of x. That was part one of the fundamental theorem. Now, problems on the homework 11, 13, and 17 were of this type, but they were a little bit harder. Because if this is anything but x, you're going to have an issue. What was part two of the fundamental theorem? This is just really quick review right now.
We could have watched the previous video, though.
We could have. Part two tells me how to evaluate this thing. How would you find and evaluate out the definite integral? This is part two of the fundamental theorem.
B.
So where f,
Big F. Big F.
why big F? What does that indicate it is?
Antiderivative.
It's the antiderivative. F of b, a curve. Wait, a straight line? A line?
Minus F.
That's why I asked. You know the one.
Did you say curve?
I thought I said, what do you call a line that's not straight? In my head is what I heard.
And the bottom, and then you do it straight.
Oh, I don't have a good.
There's no name for that?
We did that for derivatives too.
A vertical bar.
Wait, what does the textbook call it?
Why do you call it
They
a bar,
don't write
not
it.
a line?
It's to indicate this so you don't forget to use the definite integral. Okay. Well,
Is there a name for it?
I don't have a name for it. No, it just doesn't show up in this textbook. Okay, looking at these. Does everybody remember seeing these?
Yeah.
We're going to do one more difficult problem. We're just going to continue on from our examples the other day. I think we're on example D. Okay, and we're going to find a couple of these. Now, I'm going to switch this up to one that's not as bad. Let's do the integral from 2 to x squared of, I don't know, let's just call this sine x.
Should we write this?
Yeah. Now, I actually I'm going to sneak a derivative in front of that. I want to take the derivative of this guy. Sorry, I didn't realize I was going to do it until after we did it.
You should rewind, cut that part, so they don't.
I think they'll be okay. All right. As we're looking at this, the first thing, this looks kind of like one of the two parts of the fundamental theorem. It looks a lot like one of the parts, in fact. Which part? Part 1 or part 2? It looks like part 1, mostly. What's not very part 1-y about this guy?
It's going to be from 0 to x.
So I don't even care if it's 0 or anything. It just has to go from a, some constant, to some x. Now, in this case, Henry and I think Kathleen said it, they realized that this doesn't match. Right? It's x squared instead of x this time. So what we're going to do is we're going to work this thing out. And we'll keep this x. I don't want it to get too ugly. It might get a little bit ugly because I've kept it x for now. In reality, it should be a t, but we'll be okay. All right, so I want to take the derivative of this stuff. And we're going to see that maybe, just maybe, there's a shortcut to doing problems of this type. Maybe, just maybe there is. Gosh, well, what's the antiderivative of sine?
Cosine.
It's not just cosine, though.
Negative cosine.
It's negative cosine. So I have negative cosine of x. And then I'm going to introduce my vertical bar. And again, I just want to emphasize the reason that I do this is purely so that I don't forget that I'm doing the fundamental theorem. I'm using part 2 of the fundamental theorem right now. Okay, as I continue on, I'm going to let my ddx kind of hang out, and it's going to follow through. How do you actually evaluate this guy out? We have it right here. This is part 2 of the fundamental theorem. It's on the board even. F of b minus f of a. Now this is capital F already, right? We've already found it. What's b in this case?
X squared.
So this becomes negative cosine of x squared minus, and it's going to be negative cosine again. Can I just change it to a plus? Plus the cosine of 2. Now, since I'm doing a definite integral, remember, I don't care about the constant because it winds up just distributing through and falling out anyway. At this point, could I take this derivative? I think so. What's the derivative of negative cosine of x squared? So let me back that up because that sounds like a harder question. I'm just going to call him
Negative
sine. couple things happen. So we take, it's the sine of x squared. It's not just times 2, though.
So wait, so
We're just taking the derivative now. It's like I'm distributing this guy
back
through.
to the constant thing.
Okay?
So it should be negative cos x squared plus c.
So, but
Plus c minus, and this is all in parentheses, cos 2 plus c, right?
correct.
And then just,
Yep, so now when it distributes through, the c's fall out.
do we change this formula at all? Because I
Nope.
feel like this is something we might,
Nope.
if we just take as like a general thing that like we always.
The constant's
never have
irrelevant.
this- Okay.
The constant is completely irrelevant.
Because like I think if there was like an f of b minus f of a
Mhm.
plus f of c, something like that.
So if we were doing double integrals, we might have to make some adjustments. We will not, though. Okay, as I'm looking at this, if you take the derivative, I'm okay with saying it's sine of x squared now. But what do we have to do? Chain rule. What's the derivative of this inside piece?
2x.
2x. What happens with this guy? The derivative of cos 2. Yeah, it's gone, right? That's it. This is the whole derivative.
Because it's a constant.
Sorry, the derivative of a constant. Absolutely. Okay. Now we're gonna. This is it. This is the whole thing. Now notice it doesn't work quite the same as this guy. Or does it? Maybe it really does, and it just doesn't look like it yet. James,
You explain how you got the top line to the second line?
from here to here,
Just the whole problem.
I did
Well, I meant like.
I did f
Specifically the straight line.
of x squared
Oh, okay. Yeah, never mind.
minus f of 2. That's all that happened here.
Can you write that instead of the line?
From this guy? Or here? So, because the derivative of negative cos u, if you take the derivative of this thing with respect to x, where u is defined to be some function of x, this guy comes up to be, well, the derivative of cosine is negative sine. So minus a negative sign turns into a sine of u. And then anytime that you have an argument on the inside that's u, what do you have to do afterward? If you give this thing f of g of x, remember it's f prime of g of x. F prime of g of x times something else. G prime in this case, it's u prime in this case. What's the derivative of this x squared? Yep, and it's there. Okay. We're going to do one more problem of this type because I have a feeling that there is a pattern kind of peeking out through here as well. It's not quite as simple as this one, but there's definitely a pattern.
You were born in 1990?
I was born January 4th, 1990.
You're 90.
What?
I am a 90s baby.
What was the earliest year you actually remembered from the 90s?
93.
You will be 3 years old.
I feel okay, so you're saying from here to here?
Because like you're talking about the f prime g of x g prime.
Uh-huh.
But don't we have to do the derivative and
That's-
then do that?
That's what I did. I took that. So remember that if you're looking at this going, well, I'm not sure what's happening here. Remember the derivative of a difference is the difference of the derivatives, right? So I mean, I could really write this thing as d dx of negative cos x squared
The x squared just stays there.
for now, plus I'm going to say derivative of a constant, so the derivative of cosine of 2. And then as I'm looking at this thing, I realize that this is a chain rule because it's something other than just x on the inside. So when I take the derivative of this guy, I'll be right there, Sean. When I take the derivative of this guy, it becomes sine of x squared times what's the derivative of x squared? Plus what's the derivative of cosine of 2? It's just a number. What's the derivative of a constant? It's 0. So this is where I end. Sean.
Okay, so can you that first step? Can you write that in a different way?
Here?
Yeah.
How do you want me to write it?
F. Could you do? Yeah, like f a big F of x squared minus f big F 2.
If you want to, but you have to know what this is. This is the better way to write it.
Okay, what is negative? That would be big F of.
This is big F
Of what?
of whatever
Of u.
of u we can call it now, yeah.
Or like u I or.
Yeah, whatever.
UI.
I wouldn't call it u, I just say u. I wouldn't call it anything. It's just f of, I'm just going to call it f of x. It's just the antiderivative. That's all that it is. Let's do another one. Let's see if we can get this pattern to kind of peek out.
Let's do it on a round.
Sure.
How exactly do we know that it's done?
After you take the derivative. Okay, I want you guys to try one for me. On E, I want to find that's not like absolutely awful. We'll just make one up. That's fine. Okay, I want you guys to take the derivative of the following. The derivative of, let's say it's the integral from 2 to, let's say it's x cubed this time, of 2t plus 1 dt. Okay, I want you guys to take this derivative. I'm going to pause it so that you guys have a little bit of time. I'm going to show you the number of steps that it's going to take if you notice the pattern. So if you're watching this video, pause.
Oh, the count off.
Mm-hmm. If you've gotten to here, you've taken the antiderivative. Now remember, your best friend lives on page,
364.
is that right?
Yes,
It is 364. Okay. Yes, 364. Again, you are going to need these. You're going to have to memorize them. Flashcards might help. Now, as I'm looking at this, since I can color code this right here is what? So it's f of t right now, but you're absolutely right. It's the antiderivative, right? So now I'm going to take f of b minus f of a, where this is b and this is a. So now as soon as I plug this in, this gets a little bit easier, I hope. This thing becomes d dx of, what am I going to replace this t with?
X cubed.
X cubed. What's x cubed squared?
X to the 6th.
X to the 6th plus
X cubed.
x cubed.
X minus, it doesn't matter.
So it doesn't matter, but we're still going to look at it. It's minus 4 plus 2, right?
Wait, what'd you, whoa.
Okay. Yep. Let's knock out any confusion that showed up between these two steps.
Okay, I got you.
No, 4 plus 2.
That's 6.
You plug 2 into big F of t.
So when I plug in x cubed in for this, James, it becomes x cubed squared becomes my x to the 6th.
Yeah, I got that.
Okay. So we're pretty close to getting this then. Okay. Looking at this, can I actually take the derivative now, or do you want me to show you this part? Let's just clean it up. I'll do one more step. It's up to you how much you want to write here. This becomes the derivative of x to the 6th plus x cubed minus 6, right? You cannot call it x to the 9th. Definitely not. Nope, you can call it x to the 6th plus x to the 3rd. That's the best you can call it.
I recognize the shortcut.
Okay, good. I hope you do. Let's check this out one more little step. As I'm looking at this thing then, let's take the derivative. What's the derivative of x to the 6th? 6x to the 5th. Plus, what's the derivative of x cubed? 3x squared. And then I'm just going to say minus 0 because the derivative is gone. Now, you might not be able to see the exact shortcut yet, but let's clean this up a little tiny bit. What could you factor out of these things?
3x squared.
Okay, if you factor out a 3x squared, and I'm going to write it, it's going to look weird when I do it. I'm going to write the 3x squared over here for a very specific reason. What does this become? 2x to the 3rd plus 1? Now, I want to notice something, because the pattern in writing it this way, it's unnatural to write it this way, I would agree. Weird to put the 3x squared on the end, but there's a very specific reason that I've done it. Notice what happened. On the regular piece, if it just goes to x, you're right. If it just goes to x, you just replace t with x, right? If it goes to x cubed, I still replace each t, just that one in this problem, with an x cubed. And then what do I multiply by in the end?
The derivative, it's telling you what to do.
Times the derivative of whatever that was.
So you just plug it
Notice what happened here. I replaced this x with an x squared, and then I multiplied by, what's the derivative of x squared?
2x. Because the constant doesn't matter, bro.
Look.
So you plug it into the function, and then you take the derivative of b.
So, I'm going to show you guys the real generalized rule for this. I was debating on whether or not I actually want to do it. And then we're going to do one more problem.
What did you decide on?
What?
You were debating on.
Whether I want to show you this or not.
Are you going to?
I'm going to.
Right, okay.
Yeah. Okay. Here's what's really happening with this guy. if I was given, and I want to make sure I find the right one. Let's say I was given this. We're going to do one more. We're on E, F.
We just did E.
Okay.
This would be F.
So let's do one more, and we're going to work this out a little bit more. I don't know the right word for this.
Efficient.
Rigorous. Not efficient. We're going to do it rigorously to show that this does in fact work. Okay. So let's take the derivative of the following function. Let's say it's the integral from 4 to 3x squared plus 1. 4 to some 3x squared plus 1 value. And it happens to be of the square root of e to the t plus t. E to the t plus t. dt. Now, this thing looks absolutely awful, right? Because I'm going to be honest with you, you don't know how to take this integral. You don't know whose antiderivative this is. You don't even have a way to do it yet. However, if we just look at this thing, we're going to use some kind of sneaky analytic type ideas that are going to help us through this. This thing is just going to spit out something with a bunch of x's in it, right? Eventually when I do the fundamental theorem. So we're going to say the following. Let y equal, well, in this case, let's just say it is the actual integral. This is just some function that it's going to spit out at me. 3x squared plus 1 of root e to the t plus t. Now, this is the first kind of weird idea that we see because we're not used to the integral being a function necessarily, but it really is, especially if it's going to some x value up top. That is really just a function. Now, what we're really looking for then is I can use the following substitution. This thing, d dx of this, do you agree that's just dy dx now? And I'm going to even take a step further back. That is d dx of y, which notationally we really write this as dy dx. Or y prime. I'm going to call it dy dx for a very specific reason. Everybody okay with just seeing that this looks kind of like differential calculus that we did initially? dy dx is the derivative of some function y with respect to x, which is exactly what I'm doing. Now, here's an old kind of throwback idea. If, and just if, we let chain rule, and I'm just going to put a recall here, recall. If y, or y, is in terms of u, we chain rule.
I think you forgot to put U.
In terms of u, we chain rule it. Thank you. Thank you.
Oh.
Okay. Now, this was the notation that we usually used f of g of x to show chain rule. But there was another way, at least once, that we wrote it. If I have dy dx, but y is in terms of u, then this was really equal to dy du times du dx. We've definitely seen this before. This is the chain rule written in Leibniz notation instead. I like f of g of x more, but you can certainly do it this way. By expressing it in this form, what it allows us to do then is to say, well, let's take the derivative. And I'm going to switch back to blue, so we're back to the regular color. It says we'll take the derivative with respect to x, or with respect to u, of this guy. And all I'm going to do is I'm going to say 4 to u instead. I'm letting u equal this whole mess. Purely notation stuff to make it look nicer, but we're going to see it works exactly like the chain rule does. This is dy du right now, where this guy still winds up being e to the t plus t dt. So there's the first part, right? That's dy du. That's really what this is. Times du dx. Now, there's a lot going on notationally with this. But it's still just a chain rule. It's dy du times du dx. Now, this thing all of a sudden looks like the regular case of that first part of the fundamental theorem. Nope, skip it. Look at the first part of the fundamental theorem. You're good. It says this specifically, though.
F of x.
This just becomes f of x, right?
So F of U.
This is going to become f of u. Everybody okay with that? Which I know is exactly just e to the u plus u, the square root of that, times, well, what do we let u be in this case? I'm just going to write du dx here, one more step.
Oh,
What did I plug in u for, though?
3x squared
Plus, I guess that was a t, not a u there. That was a,
or no, that should be
yep, it should be u, thank you. Plus 3x squared plus 1 times what?
6x.
And all of a sudden, here's the formal way of showing that that shortcut works. Now, if you're looking at this going, nope, screw that, that's too hard, don't like it, can't think about it that way, that's okay. Because if you can apply the shortcut is really all that we're after. This is the true justification, the rigorous showing that yes, it does work. We're just using the chain rule. With that in mind,
Okay, so now that we know the formal, can you just explain it?
yeah, let's do one. Let's do one that's completely non-rigorous. Okay, let's look at the following. I want us to take the derivative. And we're going to make this one a little bit wonky. Let's take the integral from x squared to 2 of 1 over 1 plus t squared dt.
Wait, is that the lower and upper limits that you want?
Probably not, because notice how, I'll give everybody a second to get it written.
Oh, but you know you could do it.
There's,
Step
we're
by
going to, give it a second. Don't just shout it. You're right,
step.
yes.
I'm sorry.
Okay.
I'm sorry.
Yes, looking at this thing, that still looks different than our first part of the fundamental theorem, because the variable should be where? It should be on the top. If only there were an integral property that allowed those to switch. Negative. I'm going to use that property that we saw the other day, and my first little step is going to say, well, let's actually take the derivative of negative the integral from 2 to x squared of this guy, 1 over 1 plus t squared. Probably not.
Are we getting new homework for today, or are we finished?
I'm probably just going to let you finish.
But you switched.
Absolutely. This is a property that if you look in your notes from the other day, Petter, the integral from a to b of f
Oh,
is negative the integral from b to a. That's the property that I just used. Now, looking at this thing, I think I can probably just sort this out without having to actually take the integral and take the derivative. Do you know what u would be for this thing?
X squared.
It'd probably be x squared, right? So as I'm looking at this guy, well, let's sort it out. Sorry?
You gotta do quotient rule.
I don't have to do quotient rule. This looks like something I know. It's arctan. This is exactly arctan. This becomes the negative arctan of u times u prime. Now, these are the two steps that I might take. What is u in this case? Oh, I'm sorry, we're trying to skip more steps, right? You want to see it just all done right away? Okay, so if we were actually to find the arctan, then we could actually do the second fundamental theorem and we could do it and take the derivative, or we can take the shortcut. This becomes negative 1 over, what am I going to plug in for that t? X squared squared becomes x to the fourth times, what's the derivative of that x squared? 2x. Streamlined all the way through, this is really just this. And we're done. Now, if you want to, you are absolutely welcome to use the antiderivative, do f of b minus f of a, and then use the chain rule and take the derivative of it all. Or you can just take this really quick and handy shortcut. So I just want to compare it. So let's that's a good question. Notice on this one, Kayla. Notice on this one how we actually found the antiderivative and did everything, right? Like, and it wasn't terrible because this was a nice function. I'm going to do this problem again in red with our shortcut. This is something that's not just x. All I'm going to do is I'm going to look at it. I'm going to replace it with x squared. And then what is the derivative of x squared? Look at one step to get from here to here instead of all this work. Let's do it with this one as well. This time, it's not just an x, it's an x cubed. I'm going to replace each t with an x cubed. That is 2x cubed plus 1 times, what's the derivative of x cubed? Notice what we just did. Using just that shortcut, I can skip all of the actual integral and all of the actual derivative. It's always going to work out this way. Anytime that you do this, and they can look terrible, they can look absolutely awful. I don't care if you guys write this one down. Let's take the derivative with respect to x of the integral from, let's say,
No, he said you dot.
3 to x to the 5th times, I don't know, let's call this the 4th root of t minus sine t. That problem is absolutely awful. I'll tell you right now, just looking at it, I don't know how I would take that integral. But I don't need to know how I'm going to take the integral because I'm going to undo it with a different derivative anyway. It doesn't matter. Anywhere that there's a t, all I have to do is replace it with what? X to the 5th. So that becomes x to the 5th minus the sine of x to the 5th. And then I multiply this guy by what? 5x to the 4th. And look at that. Without even caring or knowing how to do the integral, I can just shortcut right through this. Now, the reason that I made us actually do the integral is we are going to have to. This is a very specific little problem that says find the derivative of this. Our focus isn't going to be just on finding the derivative. Our focus is going to be on actually evaluating out really hard and ugly integrals as we move forward. One very specific type of problem that has an easy, quick shortcut. Okay. I would assume, I don't know who found it the very first time. My guess is that Newton probably knew of it when he was doing it. If not Newton, then Riemann. It has to be one of those guys. Probably Riemann, since these are Riemann integrals in reality. Okay. With that then, that packet or the worksheet that I gave you guys at the start of class, we will do that tomorrow. Save it. Don't lose it. And you guys get the remaining 11, 12 minutes to finish up the assignment from Friday.